Hello, I'm Álvaro Calafell, and this video is the second part about the resolution of harmonic problems. In the first part, I explained the general procedure to solve numerically harmonic problems, and in this second part, I will apply this general procedure to determine harmonic voltage distortion in radial networks. So, it is important to follow this video considering the fundamentals of the general procedure presented in the first part. Remember that for solving an electrical circuit with linear and nonlinear loads supplied by non-sinusoidal waveforms, first we decompose the problem in a sum of sinusoidal waveforms of different frequencies by the Fourier series theorem. These sinusoidal waveforms were characterized by means of the phasor theory, and the nonlinear load was characterized as independent current sources by considering no harmonic interaction in their behavior. These harmonic current sources were calculated from the fundamental current calculation, an individual harmonic distortion of the nonlinear load currents. Subsequently, we applied the superposition theorem and solved independently the electric circuits for the DC, fundamental, and harmonic components of the voltage. The result is a superposition of all the obtained currents. In this video, I'm going to apply this general procedure to radial networks in order to determine the harmonic distortion of the voltage at the point of common coupling. Imagine the following simple circuit, which consists of a single-phase grid of 230 volts with a short circuit power of 1 MVA, feeds a nonlinear load of 20 kilowatts with a power factor of 0.6 lagen, and the harmonic spectrum of the currents seen below, which follows the typical 100/K pattern for each harmonic. The superposition theorem is going to be applied to the fundamental and harmonic components. The resolution of these circuits allows to determine the fundamental and harmonic voltages at the point of common coupling. The fundamental circuit has the supply voltage and the reactance of the grid calculated from the short circuit power using the well-known expression shown below, and the nonlinear load is characterized with a fundamental current source. The harmonic circuit has a harmonic voltage equal to 0 because the supply voltage is sinusoidal, and the reactance of the grid is equal to the harmonic multiplied by the fundamental reactance. We also have the harmonic current sources of the nonlinear load. These circuits are solved as follows. For the fundamental circuit, we're looking for the fundamental voltage and current. For that, we have the second Kirchhoff law in the circuit and the relation of the fundamental current consumed by the nonlinear load with the consumed active power and the power factor. However, the resolution of these equations is not trivial. We're going to solve the circuit by applying the following approximation. We consider that the voltage drop in the grid impedance is very small, and will approximate the voltage at the nonlinear load terminals as a supplied voltage. Once we know the voltage at the nonlinear load terminals, we can determine the fundamental current with the equation of the consumed power. For the harmonic circuit, we are looking for the harmonic voltages and currents. For that, we are going to characterize the harmonic circuit with the equivalent impedance of the grid and the harmonic consumed currents of the nonlinear loads. The equivalent impedance of the grid is equal to the harmonic reactance of the grid, and the harmonic currents are determined from the fundamental current and the individual harmonic distortions of the currents consumed by the nonlinear loads. Subsequently, the magnitude of the harmonic voltage at the point of common coupling is equal to the product of the equivalent impedance by the harmonic currents. We can determine with this procedure the harmonic voltages for the circuit. Finally, we can calculate the harmonic distortion at the point of common coupling from the fundamental voltage and the harmonic voltage by applying the expressions presented in the fourth video. The results are the following: the current and the impedance for each harmonic, the harmonic voltages, and individual and total harmonic distortion. It is noted that the value of the harmonic voltages is equal for each harmonic. This is due to the harmonic spectrum of the studied nonlinear load. The harmonic voltage is equal to the product of the harmonic reactance and the current consumed by the nonlinear loads. This harmonic current is equal to the fundamental current multiplied by the individual harmonic distortion of the current, which follows the typical pattern of the fundamental divided by the harmonic. So, the harmonic of the reactance and the harmonic of the current are cancelled out in this example, and the value of the harmonic voltages results independent of the harmonic. Remember that this result is only produced in this particular example, where the individual harmonic distortion of the currents consumed by the nonlinear load is equal to the fundamental divided by the harmonic. Imagine now a three-phase system with the same electric circuit topology as the example in the previous slide. By considering a balanced three-phase system, the harmonic problem will be solved in the same way as the previous single-phase circuit. But previously, we must obtain the phase-to-neutral circuit of these three-phase systems for the fundamental and harmonics. The phase-to-neutral circuit is equal to the circuits of the single-phase example, but the supply voltage is the phase-to-neutral voltage, equal to the line voltage divided by the square root of 3. The active power is equal to the total active power of the three-phase nonlinear load divided by 3. That is the power only consumed by one phase. At this point, we can proceed as in the previous examples to solve our problem. In the last example, we have a similar single-phase circuit as in the previous circuit, with a new impedance connected at the point of common coupling and a second nonlinear load. For the fundamental circuit, we have the grid with the supply voltage, the reactance of the grid, and the new impedance in parallel. And we have the nonlinear loads represented by their corresponding fundamental current sources, whose magnitudes are calculated from the consumed power and the power factor as in the first example. For the harmonic circuit, the grid only presents the harmonic reactance of the grid and the new impedance in parallel, because the supply voltage is sinusoidal and the harmonic voltage values are equal to 0. Moreover, the nonlinear loads are represented by the harmonic current sources, whose magnitudes are determined from the fundamental currents and individual harmonic distortions for each nonlinear load. To solve the harmonic circuit, we obtain the equivalent impedance of the grid with the reactance in parallel with the impedance, and we must also obtain the total harmonic current of both nonlinear loads. This total harmonic current would be equal to the sum of the harmonic currents, phasors, of each nonlinear loads, but we only know the magnitude of these currents. In this situation, we are going to assume that the phase angle of the harmonic currents is the same, and therefore, the magnitudes of the harmonic currents can be added to obtain the magnitude of the total harmonic current. This assumption is an approximation which corresponds to the worst possible case scenario because the obtained harmonic currents are the highest. The possibility of obtaining the phase angles of the harmonic currents from a random process like the Monte Carlo method also exists. With it, we could determine the phasors of the harmonic currents and calculate the harmonic voltages for all the random phase angles. After that, we must statistically study the results. However, this approach corresponds to a high level of harmonic power quality, out of the scope of this course. In this video, we have applied the general procedure studied in Part 1 for the resolution of the harmonic problem in radial networks. In the next video, Part 3, we will apply this procedure to meshed networks.